All right, so my friend Raymond and I, we're working on a rocket project right now, and we're analyzing torques. Like imagine you had a rocket going straight up, and you wanted two torques to like a rocket started going to the left or something, or to the right. You would have to use the torques. You'd have to use torques to like balance this rocket out so that it's stabilize and go up. So just gonna show you guys the project that we're working on. This is just like one part of our project. Yeah. Okay, so right now we're gonna look at imagine a rocket. We're gonna analyze the torques of a rocket going up. So imagine you have a rocket and it's going straight up, and at some point it starts to tilt to the left or to the right, or it starts to tilt to the left. So we start analyzing this by drawing a free body diagram, where we have our pivot point of our thruster is going to be represented by this dot right here in our XY plane, and we'll basically draw an angle here, theta. It can go either way depending on which direction the rocket's going, but we can represent it with a free body diagram, and it's basically what I'm drawing right here. So imagine this is the thruster pivot point. Imagine we have a thruster on a gimbal that's on a rocket, and it's able to move 360 degrees. And then we also need to know the weight force, and we need to know the force of the thruster. So our thruster can be drawn with a vector right here going towards the pivot point. We can split the thruster force into its X and Y components. So right here, looking at the free body diagram, we know that our Fy thrust needs to be bigger than the weight force, because make sure to point at the board if you can't see. The Fy thrust needs to be bigger than the weight force, and we'll know that what's causing the torque is this X component right here of the F thrust. So we can start analyzing this by looking at some torques. We know that the torque of our rocket with this angle theta can be represented by this equation right here. Torque is equal to the mass, which is the mass of the rocket, times the gravitational constant. And in this case, we need to consider the length between the center of mass, which is maybe here at this point, and that's going to change over time. That's the torque of the weight force. We have to look at a second torque, which is going to be the torque to correct the rocket. So imagine you're going straight up, right? And you have to exert another torque to counter that, the torque of the rocket. So we can represent this by force times the distance, which would be the lever arm of that torque at which it's applied. And then we have times the cosine component. Okay, so we want to find the net torque in this case. To find this angle, imagine the rocket's going straight up. We want to kind of shrink this angle so that it stabilizes and the rocket's going straight up. We can represent net torque by having delta torque is equal to the net force times the cosine of theta. Again, this cosine would be this theta right here, which would be shrinking, times the distance, which is the lever arm in this case, at which the torque is applied. So we can rearrange the equation so that we have cosine of theta is equal to net torque divided by the net force times the distance, the lever arm. And then right here we can analyze the net force, which is going to be mg. We established earlier over here that this is just the weight force going down. It would be applied at the center of mass, but so it's not accurate, like represented to scale right there. We would add that to the X component of the thrust, because that's what is causing the torque. So we have the X component of the thrust times the cosine phi right here, cosine of phi, should be this angle right here. And we can rearrange the equation so that we have theta is equal to the inverse cosine of the net torque divided by delta F, which we just expressed right here, times the lever arm, D. Example, we can use this equation to like simulate stuff. So say you have restrictions in your simulation where you only allow your rocket to go from like negative 10 degrees to 10 degrees. We can restrict that, and we can get like we can plug in a bunch of random values, and we can basically calculate our angles over a certain time period.
And this was used to calculate, to simulate the PID control.
Yeah.